In today's lab, we'll be studying reflection and refraction of light. So when light passes through the interface between two different materials or mediums, then it bends or refracts. And how much it refracts depends on the speed of light in each material. So the way we characterize this is with the index of refraction, n, which we set equal to the speed of light in a vacuum divided by the speed of light in that material. Then we can use Snell's law to relate the index of refraction and the angle of the light. So Snell's law says that n1 times sine of phi 1 is equal to n2 times sine of phi 2, where n1 and n2 are the indices of refraction of the two materials, and phi 1 and phi 2 are the angles that the light makes in those two materials. And those angles are measured relative to the normal or perpendicular line that runs through the interface. So if our interface is like this, then the perpendicular is going to be like that, and then our angle is going to be measured relative to this perpendicular. When light passes through the interface, it will either bend toward or away from the normal, and this depends on the two indices of refraction. Let's say the light starts in medium 1 and passes into medium 2, so it's going from n1 into n2. And let's say that n1 is less than n2, so it's going from a low index of refraction into a high index of refraction. In that case, as it passes through the interface, it will bend toward the normal. On the other hand, if n1 is greater than n2, so if it's going from a high index of refraction into a low index of refraction, then as it passes through the interface, it will bend away from the normal. In the second case, if the angle of incidence, or phi 1, is great enough, then the light can actually refract so far that instead of refracting and passing through the interface, it will just reflect back into medium 1. And we call that total internal reflection. The transition between refraction and total internal reflection is called the critical angle. And at this point, the refracted beam actually makes a 90-degree angle with respect to the normal, which means that rather than refracting or reflecting, it just passes along the interface. So it skims along parallel to the surface or the interface between the two mediums. So for the experiment, we're going to do two things. First of all, we'll use a laser pointer as our light source, and we'll shine it from air into water at different angles of incidence and then measure the refracted angles. And then for the second part, we're going to switch it, and we'll have it shining from water into air so we can achieve total internal reflection and then measure the critical angle. The first step is to draw two perpendicular lines on a sheet of paper. So we need one to go lengthwise, and then the other one should go across the width. So here's the two lines. This one will be the interface line, and then this one will be the normal or perpendicular line. Next, we need to add 6 lines for our angles of incidence. So we need one at 10 degrees, 20 degrees, 30 degrees, 40, 50, and 60 degrees relative to the normal. Next, I'm going to tape the paper down to the table, and that will just keep it stationary during the experiment. Now take the semicircular refraction dish, and we're going to fill this with water. Now we need to carefully align the dish with the perpendicular lines on our paper. First, use the ruler to line up the flat edge of the dish with the interface line on your paper. We can't use the 0-degree line on the built-in protractor for this because it doesn't go to the edge of the dish. Okay, that looks good, and then I'm going to slide this over until the 90-degree line on the built-in protractor lines up with the perpendicular or normal line on my paper. Okay, that looks good. And then just try not to bump this or change its position for the rest of the experiment. Now grab your laser pointer, and if you haven't already installed the batteries, then go ahead and do that now. Some of these laser pointers actually consume a small amount of power even when you're not shining the light, and to keep that from happening with mine, I just put the insert back in there. So they often come with an insert to cover the batteries, and I just put that back in there when I'm not using it. So now I can remove that, and it's ready to go. The last step in our setup is to make a simple holder for the laser pointer using some modeling clay. And this will just make it more hands-free and allow us to do the experiment easier. For the first part of the experiment, we'll be testing Snell's law, and for that we'll need to line up the laser on each of these incident angles. So at 10 degrees, 20 degrees, 30, 40, 50, and 60 degrees. The light will shine through the water and refract at the air-water interface. And then on the other side, we'll make a mark where the light comes back out, and then later we can measure those angles. Start by turning the laser on, and then aim it along the 10-degree line, and you can angle it up or down in the clay holder so that the point shines on the flat side of the refraction dish just above the intersection point of those two perpendicular lines on your paper. Then you want to check from above and see if the laser is directly over the 10-degree line. So when you look straight down, you can kind of see a little reflection at the end of the laser pointer, and it looks like it's not directly over the line, so I'm going to have to adjust that. Now if you look from above, you can see that that reflection is lined up with the 10-degree line, and that's what we want. However, now the laser point on the side of the refraction dish has moved. It's no longer in the correct spot, so I'm going to have to adjust that again, and then just keep going back and forth until they're both aligned correctly. Alright, so both of these are now aligned correctly. We've got the laser pointer directly over the 10-degree line, and then the point on the side of the refraction dish is over that intersection point. Now if we look on the other side, we should see that the laser exits perpendicular to this curved surface. So it comes in here, refracts at the flat side, travels straight through the water, and then exits perpendicular to this curved surface and continues in that same straight line. Then we need to mark a point on this side of the paper where the light is shining, and then later when we remove the refraction dish, we can trace that back to the intersection point, and that will give us our angle. If the laser only shines off the paper and you don't have a spot where you can mark it, then you may need to adjust the angle of the laser down so that more of it shines on the paper and you have a spot to mark. Now I'm just going to repeat this process with the other 5 angles, and then we'll measure them after that. At this point, you might be wondering why we can't just use the built-in protractor on the refraction dish to measure our angles. And the reason we can't is because, at least on this model, the 0-degree line doesn't line up with the edge of the dish, with the interface line. So it won't measure them correctly. Instead, we'll just have to use a regular protractor. So to measure these angles, let's move the dish out of the way. Just be careful so you don't spill the water on your paper. And then we'll use the ruler to trace the lines back from those points to the origin, or to the intersection point. I'm just going to line that up on here, and then just draw each one of those lines. Then just use the protractor and measure the angles relative to the normal line. I've measured my angles now, and also just to keep track of which side was which, I labeled them as air and water, and you don't necessarily have to do that, but it does make it easier to see where the interface line was and which side was which. Now, it might also be a good idea to add some arrows to these rays so that you can remember which direction things were going. So I think I'll put some arrows just like this to indicate the direction going from this side over to this side. For the next part, we're going to measure the critical angle, and for that we need to put the refraction dish back in place. So just carefully slide this back over your paper, and then again line it up with the ruler and the 90-degree line. Then we're going to move the laser over here to the other side and shine it through the water so that it hits that flat side again and is lined up over the intersection point. So it's just like we did before, except now it's coming from the opposite side of the dish. So right now it's refracting at the air-water interface, but in order to get the critical angle, we need to adjust the angle over here until we find the transition point between refraction and total internal reflection. If I move the laser over here, you can see that it's not refracting and we only have reflection. So we know that the critical angle has to be somewhere in between those two angles. So back over here we again have refraction, and if I keep adjusting the angle, eventually it will disappear as it skims along the air-water interface. So right here you can see that it's not quite at the critical angle, it's still refracting just a little bit, but we can adjust it just a little bit further, and as soon as that disappears, then we have achieved the critical angle. So that looks pretty good. It disappeared here, so it must be skimming along the air-water interface. But we need to make sure that the light is shining at the right spot along this flat side. And it's not quite there, so I need to adjust it just a little bit, and then again make sure that the light disappears. And I think that's it. Well, not quite. There we go. All right, that looks good. So I can see that it's hit right in the middle there above that intersection point, and then over on this side, it's gone. This next step is a little tricky. We need to mark a spot right here on the paper corresponding to the critical angle, but it's difficult to see where to put that mark. If the room is dark enough, you can see a faint reddish glow on the paper right here in front of the laser, and if you see that, then you can just put a dot right in the middle of that in line with the laser. So that's one way to do it. Another way you might do it is place the pencil right here in front of the laser and then shift it side to side until the light shines right in the middle of the pencil. And then you know you've got it in the right spot, and then just give it a little twirl or something and leave a mark on the paper. Now just move the laser and the refraction dish out of the way, and we can trace it back to the intersection point like we did before. Then again, we'll measure the angle relative to the normal line. One last thing you might want to do before we finish is take the batteries out of your laser pointer. Like I said earlier, some of these laser pointers use power even when they're not shining, so to make it last longer, you might want to take the batteries out. And that's it. So just read your instructions carefully. They will have more information than what is shared in the video, and good luck on your experiment.